In this video, we're talking about applied optimization. In this particular problem, we've been told that a farmer needs to build a rectangular enclosure of 750 square feet. So it needs to have an area of 750 square feet. We know that fencing costs $5 per foot for opposite sides and $8 per foot for the other two sides. So when we say that, here's what we mean. We have, let's say, our rectangular enclosure, and what we're indicating here when we say $5 per foot for opposite sides, if we look at these two sides here, we'll say that these two sides cost $5 per foot, so we'll say $5 per foot, and that the opposite sides cost $8 per foot. So that means that these two opposite sides here are going to cost $8 per foot, so we can indicate $8 per foot for these sides. Then we've been asked, find the dimensions that minimize the cost. So whenever we're dealing with an applied optimization problem, the first thing you need to realize is that the question is probably going to be complicated. And in order to have a consistent place to start, what you want to do is ignore everything and go directly to the word maximize or maximum or minimum. In this case, we can see minimize the cost. What we're looking to do is pull out of the problem, what are we supposed to maximize or minimize? And here we can clearly see we are supposed to minimize the cost. So we can go ahead and underline that. That's what we want to keep in mind. Whatever you're going to maximize or minimize, that's what you're going to need a function for, which means we're going to need a function for the cost of this rectangular enclosure. So how do we find a function for cost? Well, we know that the perimeter of this rectangular enclosure is going to be 2 times the length plus 2 times the width. So if we go ahead and say that this is width and this is length, the perimeter is going to be 2 times the width because we have a width here and a width here, so 2w, and we have a length here and a length here, so 2l. So the perimeter, the distance around the rectangle, is going to be 2 times the length plus 2 times the width. Well, if we know that the length is going to be $5 per foot to build, we can go ahead and say that cost is going to be equal to 5 times 2L. And we know that the width is going to be $8 per foot to build, so we can go ahead and say plus 8 times 2W. Now, when we simplify this, we're going to get 10L plus 16W. So remember that the problem told us that we had to minimize the cost. Now we have a function for cost. Our next step is always going to be, if it isn't already, get that function in terms of one variable only. Well, our cost function is in terms of 2 variables, length and width, L and W. We need to get it in terms of one variable only. So how do we do that? Well, usually the answer is in the question. In this case, we've been told a farmer needs to build a rectangular enclosure of 750 square feet. That's the clue right there. We haven't used this piece of information yet, that the area is 750 square feet. Well, remember that the area of a rectangle is area equals length times width. So if we know the area is 750, we can say instead of A equals length times width, we'll say 750 is equal to the length times the width. Now if we go ahead and solve this for W, we could solve it for either variable, but we'll solve it for W. We can say width is going to be equal to 750 divided by L when we divide both sides by L. Now we have this value here for W, 750 divided by L. We can plug it into our cost function for W here, and in that way get the cost function in terms of one variable only. So when we do that, we're going to get cost is going to be equal to 10L plus 16W, but instead of W, we're going to multiply by 750 over L, the value that we found for W. Now 16 times 750 is 12,000, so we're going to get cost equals 10L plus 12,000 divided by L. We could also call this cost is equal to 10L plus 12,000 L to the negative 1. Now we have our cost function in terms of one variable only, and we've simplified it as much as we can. When you get to that point, your next step is going to be to try to find critical points of the function, which you're going to do by taking the derivative and setting it equal to 0 and solving for the variable. So we're going to take the derivative, so that's going to be C prime. That's going to be equal to 10 because the derivative of 10L is just 10. Then we're going to pull this exponent out in front. We're going to get 12,000 times a negative 1 is a negative 12,000. L to the negative 2 when we subtract 1 from the exponent. We could also write that as C prime equals 10 minus 12,000 divided by L to the positive 2 instead of L to the negative 2. Now that we have the derivative, we want to set it equal to 0, so we'll get 0 equals 10 minus 12,000 over L squared, and we want to solve for L. In order to solve for L, we'll add 12,000 over L squared to both sides, and we'll get 12,000 over L squared is equal to 10. Multiplying both sides by L squared, we'll get 12,000 equals 10L squared. Dividing both sides by 10, we're going to get 1,200 equals L squared. And then when we take the square root of both sides, we're going to get L over here equals the square root of 1,200. Well, remember that 1,200 is the same as 400 times 3, and the square root of 400 is 20, so the square root of 1,200 is 20 square root 3. So that's the value we find for L. This is the potential critical point of the function. Because we've only found one critical point for the function, this is probably the value of L that minimizes the cost of this rectangular enclosure, but we have to prove it. The way that we're going to prove it is by using the first derivative test, and in order to use the first derivative test, all we want to do is draw a number line here, so a real simple number line, and we're going to put the value we found for L right at the center, which is 20 root 3. And 20 square root 3, if you do that on your calculator, is about 34 point something. So we'll just say 20 square root 3. What we want to do to use the first derivative test is pick values on either side of this value that are close to it. Since this is about 34 point something, we'll pick a value of 34 on this side and a value of 35 on this side. Because we're using the first derivative test, as you might imagine, what we're going to do is test these 2 points, 34 and 35, in the first derivative, c prime. So because we're going to be using c prime, I always like to put that right next to my number line to remind myself that I'm going to be testing in c prime. So what we want to do is plug 34 and 35 into c prime and see what results we get. So first we'll do 34. We'll say c prime of 34 is going to be equal to, we're plugging 34 into c prime here, so we get 10 minus 12,000 over 34 squared. Now what's important here is not the exact value of this right-hand side, but whether or not the right-hand side is positive or negative. And if we do this arithmetic here, what we see is that we get a negative value. We'll come back to that in a second, but now let's go ahead and test c prime of 35. We'll plug in 35 and get 10 minus 12,000 divided by 35 squared. And when we do this arithmetic, we see we get a positive value. Now coming back to this positive and negative value, we'll go ahead and plot these on the number line here. So we found that c prime of 34 was negative, so we'll go ahead and say negative over here. That c prime of 35 was positive, so we'll say positive over here. C prime of 34 was negative. In other words, the derivative was negative. When the derivative is negative, the original function is decreasing. So let's go ahead and draw the original function here, decreasing. C prime of 35 was positive, which means the derivative was positive. And when the derivative is positive, the original function is increasing. So we can go ahead and say decreasing, increasing. And what that shows us and what that proves is that L equals 20 root 3, or 34 point something, is a local minimum because we can literally see the function decreasing and then increasing. It's going down and then it's going up. And its lowest point right here is L equals 20 square root 3. So we've proven with the first derivative test that this value of L represents a minimum for the function. Because we tested the derivative of the cost function, c prime, it tells us that it represents a minimum of the cost function, c, and therefore that this value of L minimizes the cost. Remember, that's what we wanted to do. We wanted to minimize the cost. So this is the value for L that minimizes the cost. However, what we need to do now, and with any optimization problem, we always have to go back at the end of the problem, back to the original question and make sure that we answer the question that we were asked, because the answer to this problem may not necessarily just be L equals 20 square root 3. In this question, we've been asked, find the dimensions that minimize the cost. So we actually have to give not just a value for L, but all of the dimensions. The dimensions of the rectangle are going to be length times width, so we can say length times width is going to be equal to, for length, 20 square root 3. For width, how are we going to find width? Well, remember we had this equation over here for width. Width is equal to 750 divided by L. So to find width, if we say W equals 750 over 20 square root 3, and we reduce that fraction to its lowest terms, what we get is a value for width of 25 square root 3 all over 2. So the dimensions that minimize the cost of this rectangular enclosure are 20 root 3 by 25 root 3 over 2. So we can give this as our final answer because these are the dimensions that minimize the cost of the enclosure.